Okay, so here in Lecture 2, we're going to take a quick look at programming paradigms that the C++ language supports. We're going to talk about fundamental data types, the low-level data types that you can use within a C++ program. These are analogous to what we talked about in Python, namely int and float and stir and so on. But in C++, there are many, many more and many more specialized fundamental types. We'll also take a look at how to use arithmetic operators and how to declare and use variables in a C++ program. Okay, so as we did with Python, although it may be so long ago you don't recall, the very first program that we've written here just produces output. And that's all it does. Now we're going to be a little more ambitious and do some processing of information before we produce the output. And then finally, we're going to get really ambitious and read some input on which we'll do some processing and then eventually produce some output. Okay, so this input processing output model is a very simple, very early methodology for writing very small programs. Bjarne Stroustrup, who was the originator of C++, designed C++ as a multi-paradigm programming language. He insisted that it maintain the efficiency of the C language, which is often described as a portable assembly language, but in addition to the top-down procedural approach to programming, or the slightly higher level modular approach to programming that you can do in the C language, C++ is also designed to do object-oriented programming and generic programming using classes and templates, respectively. Okay, so here on slide 4, we have a program in a file named f2c.cpp that's just a little bit more complicated than our Hello World program from Lecture 1, in that this program is doing an arithmetic computation and then producing some output. Now, we have our cout, standard output stream object here, and we're sending a series of put-tos or insert operators to that cout object. The first thing that's displayed is the floating point value 78.0. Then, when that's done, the string degrees Fahrenheit is displayed. Notice that here in C++ we have to have spaces at the beginning and end of this string, or else there will not be any spaces in the output. Following that, we have an insert of another string, is. Now, I could, of course, have just tacked is on the end of the preceding string, but frankly, I just ran out of room on the slide, so I put is on the next line down. Then we have our fourth insert operation, and that's going to insert the result of this computation as a floating point number. And finally, our fifth insert operation is going to display the string degrees Celsius. So 78 degrees Fahrenheit is some number of degrees Celsius. Of course, here we have our new line character, which will give us our carriage return line feed, and semicolon to terminate the statement. I didn't mention this in Lecture 1, but in C++ we need the statement terminator precisely because C++ is a free format language. So unlike Python, where we can assume that the statement just ends at the end of the line unless there is some kind of statement continuation, in C++ we have to have the semicolon at the end of a simple statement to indicate that that's the end of the statement. All right, so let's give this thing a try. I'm going to pull up my Ubuntu terminal. And here is our f2c.cpp program. Let me compile this. So the name of the program is going to be just plain f2c, and f2c.cpp is the source code. And here we go. So 78 degrees Fahrenheit is 25.5556 degrees Celsius. It turns out that the result of this computation is a floating point number, and the default output representation when a floating point number is inserted into the cout standard stream output object is to display a total of 6 digits of precision. In this case, 2 of those digits are ahead of the decimal point, and 4 of the digits are after the decimal point. Okay, so the value is not precisely 25.5556, but that's the closest value rounded to 4 digits after the decimal point. Okay, so that's our little program that does a computation and displays some output. In this program, the 2 tokens, 78.0 and 32.0, are floating point literals in the same way that double quote space degrees space Fahrenheit space double quote is a string literal. In C++, the data type of a floating point literal is double, meaning double precision. That is, it occupies 64 bits of memory. That is, it's the same size and the same range of values as float in the Python language. So this may cause you some distress moving back and forth between these languages. Float in Python is the same thing as double in C++. 5 and 9 are integer literals. The 5/9 part of this computation. And in particular, these have the data type int. Now, here again, generally speaking, these are integers like ints in Python. But specifically in a C++ program, an int is usually a 32-bit integer. That is, it only contains values roughly in the range from plus and minus 2 billion. It's definitely not the same thing as int in Python, which is arbitrary precision. Actually, int in C++ is analogous to the int32 data type that we have in NumPy. Okay, so in C++, the so-called fundamental data types are the lowest level data types from which we can build higher level types. And these are typically the data types that are the most natural or fastest for the processor itself to manipulate. We've got 6 categories of fundamental types in the C++ language. There are the integer data types, and the specific data type int is one of the integer data types. There are floating point data types. The specific data type double is one of the floating point data types. Now, we don't have strings as a fundamental data type in C++, the way we do in Python. What we have instead in C++ is character data types, of which char is the most common one. And strings, we will discover, are built as arrays of chars. Okay, we do have a Boolean data type called bool. And just to annoy you, the constants here are true and false in lowercase. So if you spell them in uppercase, as you're accustomed to from Python, you'll get yelled at by the compiler. The void data type just has the keyword void, and it means that there's no value. Very often, void is used as the return type for a function that does not actually return any value. Such a function would be analogous to what's called a procedure in many other languages. And then finally, we have the null pointer data type. The specific data type there is null pointer underscore t. We'll occasionally see this underscore t suffix popping up on so-called defined data type names. And the only value of the null pointer data type is the literal null pointer. Okay, so integers, floating point numbers, characters, booleans, void, and null pointer. Those are the fundamental building blocks, the fundamental data types from which all other higher level data types are built in the C++ language. Now, here we have a complete table of all of the integer data types the C++ provides. And I'm not going to expect you to remember this, but it's important to see it once anyway. Basically, these have different ranges of values and different sizes in terms of memory that they take. The smallest integer data type is short int. Typically, a short int occupies 16 bits of memory on your system and has a very restricted range of values, roughly between plus and minus 32,000. Then we have int, which is roughly plus or minus 2 billion. Long int is 64 bits typically, possibly 128 bits on some very large processors, and its typical range of values is around plus or minus 9 quintillion. Long int will vary from one compiler to another, and depending on your compiler, it might be 32 bits in size, or it might be, more likely, 64 bits in size. It depends on the compiler. The compiler designer is allowed to choose what the size and range of each of these things are. The usual sizes are 16 bits for short, 32 bits for int, 64 bits for long. Now, these data types over on the left, short int, long int, and long int, are all signed in the sense that they are able to contain both positive and negative values. Optionally, you can use the word signed in front of each of these data types, and those mean exactly the same thing as if you just left out the word signed. Unsigned, on the other hand, does cause a very important change in behavior. An unsigned integer is exactly the same size in memory as the signed equivalent, but all of the bits in the unsigned value are treated as part of the magnitude. Many things in real life are unsigned. For example, people's ages are unsigned. We don't talk about someone being minus 2 years old 2 years before their birthday. We just say they haven't been born yet. Okay? So, whereas a short int occupies 16 bits and has a range of values roughly between plus and minus 32,000, an unsigned short int also occupies exactly the same number of bits, 16 bits, but its minimum value is 0 and its maximum value is going to be double 32,000. Specifically, it's going to be 65,535, which happens to be 2 to the 16th power minus 1. Okay? Now, for an int, which is 32 bits, the signed integer has values between plus and minus 2 billion. The unsigned integer is also 32 bits and has values between 0 and a little bit more than 4 billion, and so on. Okay, so the word signed is redundant and is just basically included for historical committee bureaucratic reasons. Unsigned means that you're treating all of the bits of data within the object as magnitude, and you don't have any negative values for unsigned integers. In terms of integer literals, it turns out that we have 3 different number bases we can use for specifying integer literals or integer constant values. Decimal is base 10, and that's what we're used to. So 1 means 1, 2303 means 2303, 14 means 14, etc. We can also specify values in octal, that is base 8, or in hexadecimal, base 16, in the C++ language. If the leading digit on an integer literal is 0, that means that the value is taken to be in base 8, an octal value. And so 0 is just equal to 0. The fact that it's base 8 is somewhat irrelevant. 017, on the other hand, means 1 times 8 plus 7. So this is a 1 in the 8th place and a 7 in the 1's place, which is the equivalent to 15 in base 10. 177 is a 1 in the 64's place. Okay, so 1 times 8 squared plus 7 times 8 plus 7, which gives me 127. Octal digits are a little bit hard for a lot of people to understand. More common are hexadecimal digits if you want to represent patterns of bits or locations in memory or what have you. Hexadecimal is base 16. To represent a hexadecimal integer, you start out with either a 0x where the x is in lowercase or a 0x where the x is in uppercase. Then you use the digits 0 through 9 as usual to represent the values 0 through 9. And the letters A through F, either in lowercase or uppercase again, to represent values 10 through 15. Okay, so 0xf is the hexadecimal way of representing a value that's the same pattern of bits as decimal 15. Hex FF, on the other hand, is the same as decimal 255. Okay, so if you find yourself at some point in the future having to deal with things like patterns of bits, patterns of flags, machine addresses, that kind of thing, you'll pick up hexadecimal relatively quickly. Since we're working in finance, most of the time we're only going to be caring about decimal integers represented in base 10. Okay, so those are the integer data types. Now, as far as floating point types, C++ provides 3 different floating point data types. Float, which unlike Python, is a single precision floating point value. It only occupies 4 bytes of memory. It only guarantees 6 digits of precision, and it has a quite narrow range of magnitudes, 10 to the plus or minus 38 power. Double in C++ is analogous to float in Python. That is, it stands for a double precision floating point number. It occupies 8 bytes of memory, guarantees at least 14 digits of precision, and has a range of magnitudes of 10 to the plus or minus 308. Long double, depending on your compiler, may or may not be what's called extended precision. So it may or may not occupy 16 bytes, give you a minimum of 19 digits of precision and a much wider range of magnitudes, 10 to the plus or minus 1024. Again, it's up to the developer of the compiler to decide the specific implementation details for these 3 floating point types. In older C++ compilers, floating point literals are in base 10. C++ 17 did actually introduce hexadecimal notation for floating point literals. And a floating point literal basically has to include either a decimal point and or a base 10 exponent. So 0 point is a valid floating point literal. Its data type is double, and its value is 0.0. In this next example, we have a base 10 exponent. 123e6 is treated as 123 times 10 to the 6th power. And again, that is a double value, 123.0 times 10 to the 6th power. Okay, so in these next 6, we have either a decimal point or an exponent or both. In most cases, or in several cases, we have both. So these are all double precision floating point literals. Now these last 2, where we don't have a decimal point or an exponent, that's just an int with a value of 0 in this particular case. And if you just give a decimal point all by itself, that's not valid. So that's an illegal syntax. All right, so there's the rules for floating point literals. The char data type is able to store any single character in your system's native character set. And on our systems, this is going to be the so-called ASCII character set. Now, in C++ and C, by definition, a character occupies 1 byte of memory. So however many bits of memory a char occupies on your machine defines what your C++ compiler thinks of as a byte of memory. Depending on the system, a char might be a signed value or an unsigned value. It's not defined by the language whether a char is a signed value or an unsigned value, but fortunately, the ASCII characters live in this range from 0 to 127, and that range, 0 to 127, is guaranteed to exist whether characters are signed or unsigned. Now, you can specifically declare that you want a char to be signed, which guarantees that it will have a range from -128 to 127. Or you can explicitly declare that you want your char to be unsigned, which will guarantee that it has a value between 0 and 255, assuming that you have 8-bit bytes on your machine, which is virtually guaranteed on modern systems. Okay, but whether a char on your system is signed by default or unsigned by default, fortunately, any of the ASCII characters that we need for our source code in C++ will be able to fit without change into a char variable. There are some defined data types for multi-byte character sets. There's the wcar_t, the car16_t, car32_t. We're simply going to stay away from those. If you need characters that are outside of ASCII or that are outside of the UTF-8 character set, you can grovel around in the documentation to find out details about how these other things work. In C++, everything is very close to the machine. And character data types, it turns out, are a subset, if you will, of the integer data types. And in fact, you can use characters in arithmetic computations, which may seem a little strange. If you want to see a good ASCII character set table, there's one on the cppreference.com website. Let me go ahead and pull that up in a browser. Okay, so I've pulled that up in a Chrome web browser. This may be a little bit hard to read. There are 128 characters in the ASCII character set with decimal values ranging from 0 up to 127. You can think of these as being divided into 4 sets of 32. The first set of 32 is control characters. And within this collection of control characters are things like the backspace character, the line feed character, which is also called the new line character, the carriage return character, and various other things. The next set of 32 is mostly punctuation mark characters and the digits between 0 and 9. Notice for the character 0, the decimal character 0, the digit character 0, the decimal code for that is 48. And the decimal code for 9 is 57. Okay, so if I were to say, and let me actually do this in a little program. I'm going to say, let me create a file called car9 plus car0. All right, so I'm going to include, well, let me get the name of the file in here. We'll include IOStream as we always do. We're going to say using namespace standard to use the standard library facilities as a default. And we're going to create ourselves a main function. And in here we're going to say cout character 0. Now the way you represent a single character is to use single quotes. And if I say single quote A, single quote, that represents the little a. Single quote capital A, single quote, represents the character capital A. Single quote 9, single quote, represents the character, the decimal character 9. And in my program, single character 0 represents the character 0. Actually, the name of my program is char9 plus char0. So let me change this to a 9. And then I'm going to add character 0. And then we will display a new line. Okay, so what I'm doing here is I'm adding two characters together. And that's permitted in C++. What's going to happen is that the character code for 9, which I said was 57, is going to be added to the character code for 0, which I said was 48. And I'm going to get 57 plus 48 is 105 as my result. Let's see whether that actually does what I claim. So that's my program, and then char9 plus car0.cpp is my code, and I will execute car9 plus car0, and yes, I get 105. Okay, let me flip back to my ASCII table in my browser to confirm why that makes sense. All right, so if we look, here's character 0, which, if it's treated as an integer, is going to be equivalent to 48. And character 9, which, if it's treated as an integer, is going to be 57. If I add 48 and 57, I end up with the integer value 105 as an int. And that got displayed, that got printed out as an int value of 105. Okay, well, in some sense, that's kind of a, that's a trick. Normally, we would just display characters or put them together in strings. All right, so here, rather than trying to add these characters together, I'm simply going to use cout to display the character 9, then display a space, then display a 0, and then display a new line. Now, the single quotes are not going to be displayed as part of the output. Okay, so in my first cout statement, I got a 9, a character 9, a space character, a character 0, and then a new line character. So that's my first line of output. And then my second line of output is the result of this computation. Okay, so this is entirely unlike Python. In Python, single quotes are just an alternate way of defining a string. Whereas in C++, single quotes are used to represent a single character, not a string of characters. Okay, so looking back at slide 14, a little a is represented as single quote, little a, single quote, capital A as single quote, capital A, single quote. A space character is represented as single quote, space, single quote. 9 in quotes to represent a 9 character. And then here we have, as another example, a semicolon character in single quotes. We can represent a single new line character using the backslash notation that we're familiar with from Python, except here this is a single character rather than a string containing a new line. Likewise, here we have a horizontal tab character. Okay, now the single quote has the special meaning that it contains a char. The double quote has a special meaning that it contains a string of chars. The backslash is used in this backslash notation, and it turns out that the question mark also has a special meaning. So to represent any of these four characters, the single quote, the double quote, the backslash, or the question mark, you have to say quote and then backslash on the character and then quote. Okay. So we've now taken a look at the integer data types, the floating point data types, the char data type. Next, we're going to take a look at the Boolean data type, bool, which has the two possible values, true and false. The equality, relational, and logical operators in C++ are very similar to the ones in Python, not exactly the same. For example, the greater than symbol or the less than symbol is how you do a greater than or a less than comparison, respectively. 5 greater than 4 results in a Boolean value of true. 5 less than 4 is a Boolean value of false. And just like characters, technically bool is one of the integer data types. So you can add two trues together and get an integer value of 2. The void data type has no possible values, and it also occupies no memory on the system. Most of the time, the word void is used as the return type for a function that does not actually return any value. Sometimes you'll also see void used in the context of a pointer to void. That is, the address of some data where we don't fully understand the form of that data. So we can just think of that as being an address of or a pointer to some blob of data where we'll figure out the details about that data later on. So we'll have a lot more to say about void as we go. We'll also have a lot more to say about the concept of pointers as we go. And null pointer, the token null pointer, is used to indicate that a pointer does not point at anything. All right, so these are getting a little bit ahead of the game. So we've got our 6 classifications of fundamental data types. We've got the integer data types, of which there are 12 different specific ones. We've got the floating point data types, of which there are 3 specific ones. We've got the char data type, which also includes signed and unsigned variants. Then we have the bool data type, the void data type, and the null pointer data type. All of the other data types in a C++ program are built from those 6 fundamental data types. Now, as I said, I'm not going to make you memorize that entire table of 12 integer data types. I'm likewise not going to force you to remember the details of the 3 different floating point data types. Almost entirely, the data types that we will use in our course and the data types that you see in most C++ programs are char, to represent one individual character value, int, to represent an integer value in a restricted range roughly between plus and minus 2 billion, double, to represent a double precision floating point value with a guaranteed 14 digits of precision and a range of exponents of roughly plus or minus 308. Then we've got bool for true false. Occasionally we will need to use unsigned integers, because it turns out that there are certain things that can't be negative, and we're going to see various unsigned data types pop up, particularly with respect to library functions that we're going to call in the future. We're also going to use the void data type and the specific literal value null pointer. All right, so these are the specific data types that you should understand quite well. And in cppreference.com is a good description of these things.